This is the last topic in classification, which name is neural networks. In fact, this technique has been received great attention from the related society because of its powerful performance. But especially nowadays, the reason that it has been uh, received a great attention is that because of the deep learning and deep neural network, deep deep learning. I think some of you may hear this name before, but the thing is that this deep neural network, the simplest structure, basic structure of the deep neural network is a shallow neural network that we're gonna talk about this class. So to understand the deep neural network, you should understand this simple neural network structure. Then it would help you a lot to understand the deep neural network, even though in this data mining class, we do not talk about the deep neural network, but I think later, after this semester, this lecture would help you a lot to, if some of you want to study about the deep neural network, then I think this lecture could be a good foundation to understand the deep neural network. So in this class, this lecture slide is pretty much talking about how we train a neural network based on the training data set. And even though all those explanations are based on the classification task, in fact, this technique can be used for both classification and regression. The way of training a neural network for classification and regression is the same. The way of training is the same. We just minimize the error. That's the way of training neural network, and the detailed explanations will be shown throughout this lecture slide. So to understand how we train a neural network, we should know the nonlinear optimization, because training a neural network is in fact solving a nonlinear optimization problem. So the first few slides is talking about very brief explanation about nonlinear optimization problem, especially this case, unconstrained nonlinear optimization problem. Here the unconstrained means we don't have any constraints on x variable, and the general form of in fact this one is a general form of optimization problem. We want to find the value of x that minimize this function here. This f function is called objective function. Objective function. And here the function f is a function that is mapping a p-dimensional value to one-dimensional space. Okay, so you can just think of a general function f that receives a p input values in general that is expressed by a vector, and it returns a single scalar value. So this f is just function that you have been seeing a lot, and that f function in nonlinear optimization context, that must be continuously differentiable. So if that f is a convex and differentiable function, then it has just only one extremum. It has only one optimal solution, and we can find that optimal solution by simply solving this normal equation. So what we do is we just find the first order derivative, which is called gradient, in fact, the first partial derivative of this x function, and we set that gradient to 0 and solve this normal equation. Please notice that here this part is a vector, and this 0 is also a vector of the length of which length is p in because we are talking about p-dimensional input. So this one is a vector which length is p, and this one is also vector which length is p. So simply, the simplest case of f is the case where p equals to 1, and the most simple example is f equals to x squared. So what is the value of x that minimize this f function? What you do is we just take the first derivative of this f function, df over dx, that is, what is that? That is 2 times x, and we set this to 0 and then find the value of x. X is 0. So this one is the optimal solution. Okay, so this is a one-dimensional case, and another case is in the case of two x variables, then we can think this kind of function f, that is x1 squared plus x2 squared. That must be, looks like, this is a convex function, so this function looks like this one. Okay, so there is only one extremum that minimizes this f function. So what we do to find the optimal solution that minimizes this function is we take the first order partial derivative of this f function with respect to x1 and with respect to x2. So round f over round x1, what is this one? That is 2x1, and round f over round x2 is 2x2. We set these two vectors to 0 and solve these two equations, then the optimal solution is x1 equals 0, x2 equals to 0. So this one is the optimal solution that minimizes this f function. Okay, so I think you can understand the meaning of this sentence. If x is a convex function and that is differentiable, then the way of finding optimal solution is very simple. We take the first derivative of f function and set that gradient to 0 and solve this normal equation. Okay, and so far we talked about the minimization case, but if we want to find this case, then we can simply, this optimization problem is equivalent to mean minus fx. So every maximization problem can be transformed into minimization problem by just multiplying -1 to that objective function. Okay, so in this slide we are talking about the convex function case, but if this f function is not a convex function, then we cannot find the optimal solution in that way. So what we can do is actually we can employ several different, there are several different methods to solve the unconstrained nonlinear optimization problem. But what we're going to talk about is a gradient descent method, which is one of the most often used method to solve nonlinear optimization problems. So let's take a look at this figure. This is a one-dimensional case. There is only one x value, and this line is the function f that we want to minimize. So the optimal solution is here. The value of x that minimizes this f function is here, because we cannot find, if we take the if we solve this optimization problem in this way, the way shown in this slide, then there are 2 points that has the that has the zero gradient, zero slope is here and here. So instead of finding that way, what we generally do, what this gradient descent method does is we start from a randomly chosen initial solution x0. So that is initial solution, or sometimes we say a starting point x0. So we just randomly pick up a value x0 on this space, and then we find the first derivative of f function. Then that gives us a direction, especially this negative gradient. So this is a first derivative, and that is also called gradient. That is a direction that reduces this f function value. So we can get a hint. Okay, let us move to this way to reduce the value of x, the value of f. So we move a little bit, and then the descent using that gradient information. This sentence means what I just taught to you. So we move a little to some value, which is named as x1 from x0, and then find the gradient again, and then move again until we reach to this point, which is an optimal solution. So we move to this direction, and we must stop here. Okay, so that's the basic idea of a gradient descent method. Then the updating rule of x is shown here. So the next value of x, t plus 1th x, is defined by this one. The next value of x is defined by the current value of x minus is first derivative value at xt and times some constant which is called learning rate. Anyways, the next value of x is updated by this one. So let us say that here this value is xt, and we want to find the next value, which is xt plus 1, that reduced this f function. Let us say that this curve is f. Then if we take the first derivative, the gradient of information at this point, then we can see that this f prime, the sign of s prime, is greater than 0, right? Because the slope here at this point is positive, right? So what you do is, because this value is positive, we have to decrease to reach to this point. We have to move in this way. That's why we multiply -1 to this gradient information. Okay, and here eta is determines how much we move. Okay, so if this value is big, we move a lot. If this value is small, if eta is small, we move a little. Okay, and let us take a look at this case. So if xt is here, then the slope on this f function is negative, right? So f prime is less than 0. So by multiplying -1, we can increase the current value of xt. It means that we can move this xt to this direction. Okay, so now I think you can understand this update rule. Okay, so assume that t plus 1 is here. Here's xt plus 1. Then the next value is computed by the same way. So xt plus 2 equals to xt minus f prime xt plus 1 times eta. Okay, so please notice that this t plus 1 is not an exponent. It just indicates an index, the sequence of x values. Okay, so here is an example. We want to minimize this x to the 4. We want to minimize this function. That function looks like this one. And then the initial starting point, initial solution, actually that is chosen random, and let us just pick up 2 as the initial solution. Then the next value, the x1, the next value is computed by the formula shown in this slide. So because the x0 is 2, here we put the 2, and is first derivative is 4x to the 3. So we just put here 2, then the value is, what is that? 4 times 8, 32. And the eta is set to, actually that is the value of eta is chosen by your choice. But usually we should set this value to very small value. In this example, it was set to 0.02, then it becomes what? It becomes 0.32, and 2 minus 0.32 becomes 1.68, right? So we move from 2 to 1.68. Then the next value is computed by the same way. The next value is computed by the same way, yes. So here the x1 is what? 1.68, and we must be able, we can calculate the first derivative value at this point. I don't know that value. That value is 4 times 16823. Okay, so to calculate this value and put that value here, and eta is 0.01, then the result is 1.4903. okay, this value. So we can move a little bit here, and we'll repeat this update again and again, then we can reach to this optimal solution. But this figure shows 200 repetitions, and then you can see that at the beginning it moves quite big, but the amount of movement decreases. Why? Because as we approach it to this optimal solution, the slope, this one, the first derivative value becomes is very close to 0, right? The slope decreases as we approach to this optimal solution. So as we approach to this optimal solution, we have to repeat and repeat more to reach to this optimal solution. Even though we repeat 200 times, we cannot reach to the optimal solution yet. This algorithm is not converged yet. Okay, so to reach to the optimal solution for the faster approach to this optimal solution, what you can do is we set this eta to a larger number. So let us say that if we set eta to 0.03, which is greater than this one, 0.01, then you can see that it approaches to the optimal solution faster, but still, has the same problem, as we reach to this 0 point. Okay, the slope, because of this one, the slope becomes quite close to the 0. So still we have to repeat many times. But anyways, that's the way that we can reach to the optimal solution faster. But the thing is that if we set that eta to quite large number, we cannot reach to this optimal solution. We're just wondering, because if we move a lot, then the next value becomes here, for example, and we wondering, and we cannot compose it to this optimal solution. Do you understand that? So that's why we usually set this eta value to very small number. Even though we repeat so many times, we do not we can eventually converge it to this optimal solution. So please notice that this eta value, the value of eta is set to pretty small number. Okay, that's the gradient descent method to solve a nonlinear optimization problem. And one more thing that I want to mention is from this gradient descent method is that, so in this example, if we start from if we start from this point, then we'll reach to this point. But if we start from this point, then we converge at this point. So this is not an optimal solution because this point is the value of x at this point returns a smaller value of f, right? So usually if we use gradient descent method to solve a nonlinear optimization problem where the f function is not convex, then what we do is we do multiple initial points. We try not just this x1, x0. We randomly generate. We try multiple initial points. Then we can converge. For example, let me draw a more complex shape like this. Then if we start from here, then it converges to this point. If we start from here, it converges to this point. If we start from here, then it converges to here. Then we can find all those local minima. Okay, local minimum points, minimum solutions. After that, compare the f values at all those local minimum points, and then return the x value that is corresponding to minimum f value. Okay, that is the way of using the gradient descent method to solve an unconstrained nonlinear optimization problem where this objective function is not a convex. Okay. I just spent more than 20 minutes to explaining about this nonlinear optimization problem. Anyway, again, training logistic regression is a solving nonlinear optimization problem. That's why I spent this lots of time. And let us take a look at this function, hx, that is defined by this one. In fact, this h function is a logistic regression. So instead of f, I just use h here. And this W transpose x is just a vector expression. So this W transpose x is W0 plus W1 x1 plus dot 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 plus WP xp. Okay, so this one is just a vector expression of linear combination of x variables, and here this one is constant, this one is the coefficient. Previously in logistic regression context we used beta, okay, from beta 0, beta 1 to beta p, okay, and this one is in fact is equivalent to what? That is 1 plus exponential W transpose, because we have minus here, W here we don't have minus, W transpose x 1, these two are equivalent, right? By rewriting this one, 1 plus exponential W transpose x and exponential W transpose x, right? So this term is equivalent to this one, and we saw this formula in logistic regression class. Okay, so now you can see that this function is in fact logistic regression. Then this figure shown in this slide is a case of only one x variable. There is only one x, and there are two classes. One is red class and the other one is blue class. Then if we train a logistic regression model based on this 1, 2, 3, 4, 5, 6, 7, 8, 9, these 10 data points, then you're gonna get this yellow colored S-shaped curve, okay? And the way of classification is shown here. If the value of h is less is greater than or equal to or greater than 0.5, then we classify an object into red class, and if h value is less than 0.5, we classify, right? So here this one is the decision threshold value, and this one is the decision boundary. Okay, the way of classification is this one, as you already know. Then, in fact, this logistic regression can be decomposed into two parts. The first one, so two steps for evaluation. The first one is the linear combination of x variables. Okay, this one, W transpose x. So we can express in this way, and here, because here we use x0 equals to 1. Okay, so this expression is equivalent to this expression. Okay, just the first evaluation, the first step is the linear combination of inputs, and the second step, the second evaluation is a nonlinear transformation of S. So let us set this linear combination as a S, and we just put this scalar to this function, 1 over 1 plus exponential minus s. Okay, this function is same as this one, and again this one is a logistic regression. So this function is called, in fact this one is called logit function. Another name is sigmoid function. In computer science field, this one is called the sigmoid function, and because in fact this neural network was developed in the computer science field, we're going to use this term to indicate this function. Okay, and if we express this logistic regression in a graphical form, then we can express like this. Okay, here is the x1, x2 to x. Okay, let us, instead of p, let us use, from now on, let us use d. Okay, so there are d inputs, d x variables from x1 to xd, and here is a 1, because to express a scalar, what you do is we just multiply these two, and these two, and these two, and then make the summation. That is a linear combination of input variables. And then here f is a sigmoid function. We just pass that s value to this f, then the y value becomes an output of logistic regression. Okay, so this one is a graphical expression of logistic regression. Then actually it has another name. This logistic regression has another name in computer science field, that is perceptron. So the logistic regression may be called an artificial neuron, and computer scientists long time ago, they developed this method motivated by human neurons and human perceptrons, and the way of transferring the the signals in our brain. So the logistic regression was developed and used in statistics field, but neural network and perceptron was used in computer science field. Okay, but both are the same. So another name is perceptron, and it mimics the function of neuron. So logistic regression is using one perceptron. But the thing is that instead of just one perceptron, we can use 2 perceptrons, 3 perceptrons, and 4 perceptrons. And the general graphical representation of multiple perceptrons is given here. So this is the same. We have x1, x2, and xd, and this arc is representing a weight, a coefficient, or some scalar value that is multiplied to each of the inputs. Okay, we make summation just like this, summation. So you can even though there's only one circle here, you can think this one as a two steps. The first one is the summation of those values multiplied by each of the weights, and then pass through the f value. Okay, so this node indicates two steps. This one also indicates two steps, and it is same for all those nodes. The summation and sigmoid function, summation and sigmoid function, summation and sigmoid function. Okay, so this is a general form of multiple perceptrons and multi-layer perceptrons. So this part, which is corresponding to the input variables, that is called input layer, in Korean 은닉층. And then I'm sorry, 입력층. And this part is called, this layer is called hidden layer, in Korean 은닉층. And then this part is called output layer. Okay, so the logistic regression is only this part, but you can make many more, and then we can cascade again. We can make the weighted summation of all those h values and then pass through f, and then we can repeat these procedures many more times. So again, let us just remember the names of this structure. Input layer, hidden layer, and output layer. And in fact, you can make another hidden layer here between hidden layer and output layer. You can make more, two hidden layers and 3 hidden layers and 4 hidden layers. If we have quite many hidden layers, that case is called deep neural network. Okay, so this one is kind of shallow neural network. And the number of hidden nodes, actually that is given here, given in this slide. The number of hidden nodes, in fact, there are p hidden nodes in this figure, but number of hidden nodes is determined by your choice. If you place just 2 hidden nodes, that's okay. If you just want to place put 5 hidden nodes, that is also okay. But the number of input node is determined by the dimension of input variables, x variables, that we have in a training set. And the number of output node is determined by the number of outputs given in the training set. In the case of classification, if we have 3 classes, then we place 3 output nodes. If we have 2 classes, then we put 2 input nodes, 2 output nodes, or we can even use only 1 output node. If there are 4 classes, then 4 output nodes. Okay, so the number of output nodes, that is determined by the dependent variables that we have. But this case, okay, that's it. Anyways, in the regression case, you can just put just 1 output node. In regression case, if you have only 1 response variable. Okay, again, the input layer, hidden layer, and output layer, input nodes and hidden nodes and output nodes. So input layer simply passes the input values to the next layer, which is a hidden layer, and the number of inputs equal to the number of input nodes. And in hidden layer, there can be several hidden layers, and then in one hidden layer there can be several hidden nodes at each hidden layer. So again, the number of hidden nodes and the number of hidden layers, they can be determined by your choice. And the number of outputs, that becomes the number of output nodes. And here is an example of two perceptrons. So we have two, you can see that we have two inputs, x1 and x2, and then we have one logistic regression and the other logistic regression, and their outputs are also connected by the one more perceptron, and then the final output becomes the after passing through this second perceptrons. And then so this is a case of two perceptrons, and this example again has two x variables. And for example, here this w sub 1 is the weight multiplied to this x1 value, and that connects x1, and this one is connects between x1 and h1, which is the first hidden node. And another example is w sub 2 is the weight is which is multiplied to x2, and that is on the value connecting between x2 and h1. So actually, in fact, we don't know those values. We don't know these values. And training a neural net means finding those values, finding all those values, okay? And in this structure, so the h1, the value of the first hidden node, becomes this one, right? If we use the sigmoid function, then the form of h1 becomes this one, 1 plus exponential minus w transpose x, right? And then x2 becomes this one. So here x1 and x2, we have the x1 and x2 in both h1 and h2. And because those h1 and h2, they are formed as a linear combination with those v coefficients, right? So the y becomes in this form, 1 plus exponential minus something, the v transpose h. Okay, so if we put this formula here and h2 here, then finally the y can be expressed in terms of x1 and x2. Okay, so this structure, this graphical representation, is in fact this one. So what you can see from this these two slides that is that in fact actually this one is one example of neural network. Neural network can be expressed as a closed form with respect to x1 and x2. So please remember that because out there people really don't know about whether or not this neural net is in fact a formula. Only few, to the best of my knowledge, only few people know about this. So please remember that neural network can be expressed as a closed form with respect to input variables. But the thing is that with this very simple, with this very simple, I'm sorry, simple structure, even for this very simple structure, the formula becomes very complex, right? So imagine that the case where we have more x values and more hidden nodes, then this formula becomes more and more complex, quite complex formula. But the thing is that it can be expressed as a closed form. And what these two perceptrons can do that in fact one perceptron cannot do is this one. Here's an example which is called XOR problem. This is a classification problem. There are two input. Please take a look at. Please take a look at this figure. We have two x variables, and there are 4 data points, and two classes, red class and blue class. So here the question is, can we classify these 4 data points correctly with 100% accuracy by just drawing a straight line? The answer is no, right? If we draw a line here, then this one will be misclassified as a red class, and if we draw line this way, then this one will be misclassified as blue class. So we cannot make 100% accurate classifier by a straight line, but which means that the one straight line is a logistic regression, right? But the thing is that by the two perceptrons, we can make a 100% accurate classification model just like this. So let us assume that this W11 value is 1. Here this value is 1. And W21 is 1. W21 is this one. This one is 1. And W01 is minus 1.5. So this value is 0 minus 0. Minus 1.5. Then the first data points, this one at 0 and 0, its value becomes the H1 value. I'm sorry, this is typo here. H1, H2. Okay. So multiply this one. 1 times 0 plus 1 times 0 minus 1.5 becomes negative 1.5, right? And this observation, which is this one, is 1 times 0 plus 1 times 1 minus 1.5 becomes minus 0.5, right? And then we can make the same calculation for the remaining 2 data points, and then we're gonna get the linearly combined value. And because this value is negative, then actually in fact in this case we use the step function. So let us say that if this linearly combined value is negative, then we transform that value into 0, and that if this value is positive, then we transform that value into 1. Then because this one is negative, the H1 value, H1 value is 0, and 0, negative 0, positive 1. Okay, so in this case, actually, this H function is a 0 or 1 if x is less than 0, equal to or less than 0, then it returns 0, and if x value is greater than 0, then it returns 1. Actually, this is called step function. In fact, in this case, instead of the sigmoid function, we are using step function. So the function h looks like this one. This function. If the input value is positive, it returns 1, and if the input value is negative, then it returns 0. Okay, so we are using this step function instead of sigmoid function. And then if the W12 and W22 is 1 and 1, and W sub 02 is minus 0.5, then they are these values. This one, and this one, and this one. Okay, let us assume that those values are given. And then by the same rule, this 0.0 H2 value becomes 0, and for this observation, because the value in this case, right, 1 times 0 plus 1 times 1 minus 0.5 becomes 0.5, which is greater than greater than 0. So the h2 value becomes 1. We can transform like this. So we can transform into another space of h1, h2. We can mapping those 4 data points into another space. So this point goes to here, and this point goes to here, and this point, its original coordinates is 1 and 0, but the h1 is 0 and h2 is 1, right? So it goes to this way, this data point at this point on this space, and this point goes to here. Then not this space, but in this space, actually we can make a 100% accurate linear classifier by drawing this line. Okay, so that is shown by here. So let us also assume that we found the value of v11, v21, v01 like this. Then this value is linearly combined value. This is a value from linear combination, and then because this value is negative, y value becomes 0, and actually this is, yes, this is y, and here is h1 and h2, and this one is positive 1, negative 0. Then the thing is that let us compare this output from neural network with true class value. 0, 0 was lead. This one is, let us set like this. Lead class is 0, and blue class is 1. Then this one is lead 0, 1, 1, 0, right? And its output is the same. So the predicted class is exactly matching to this original class. Okay, so then the thing is that how we find those weights, those values, that is the way of training neural network. We're gonna take a look at that. So what a neural network can do, but a logistic regression cannot do, is we can make even for this XOR example, XOR problem, we can make 100 accurate classification. We can make 100% accurate classifier. Okay, so this part we can interpret like this. This part is a part of this part is a logistic regression, and this part is another logistic regression, and this part plays a role of a kind of AND operation. So you can think like here is a S-shaped surface and another S-shaped surface in three-dimensional space. Okay, so we can make a so this part is the blue class area, and this part is red class area. Okay, so can you say that difference between logistic regression and two perceptrons, which is an example of a neural network? I think you can see the difference. Okay,